Well, I think it's about time we get into some matrix row operations. Alright, this is like the heart of linear algebra right here. Alright, so this is when you really start getting into what linear algebra is really about and what you're going to be doing for the rest of your semester. So you've probably seen some systems of linear equations before, and you've probably used substitution or elimination to solve them. Right, but you know that they can get really complicated and really messy, especially if you have more than two equations and more than two variables. And linear algebra makes that really easy for us to solve. And we solve them by using a matrix. Alright, so what we're going to do is pretty much remove all of the variables from the system of linear equations and organize them in a specific way so we don't forget where they were. Okay, so that probably doesn't really make much sense, but I'll show you here. So since the x's are farthest to the left, we're just going to keep them in that position. Okay, we're going to put all the coefficients of the x variable in the left column. Okay, so we do 3, 4, and 1. Like that, and that is our left column of our matrix. The middle column is going to be our y variable. So in the first equation we have a minus y, so we're going to have a negative 9, since it's a minus and not a plus. In our second equation we don't even have a y variable, so we're going to put a 0 here. And in our last equation we have a 7. So our next column we have 6z, there's 2z in this our second equation, and there's no z in our third equation. So that is what our coefficient matrix looks like. Alright, but you know you need to include the right side of the equation if you're going to solve this system. So what we're going to do is we're going to add to our coefficient matrix with what we call an augmented matrix with the solutions on the right side like so. And remember, the order corresponds to the order of the system that we already have. So since the first equation has a 12 on the right side, we put a 12 in the first spot. And since the 6 is in our second equation, we put a 6 in the second spot. Since the 14 is in our third equation, we put the 14 in our third spot. And remember, those should correspond to the coefficients here as well. So both the columns and the rows correspond to each other. Whoops. Alright, so now that we have our augmented matrix set up, now what can we do to solve the equations? So the first thing you can do is scale a row. So if you see that something is divisible by a certain number, like you can see the first row here, all of those numbers are divisible by 3. So you could divide, or we say multiply it by 1/3. We say 1/3 times row 1, and then we'll make a new matrix with our new values in it. Then all the rest of the values stay the same, right? So all I did there is multiply each component of row 1 by 1/3. So 3 times 1/3 is 1, negative 9 times 1/3 is negative 3, 6 times 1/3 is 2, and 12 times 1/3 is 4. So that's scaling, alright? We just multiply it by some scalar value. But why are you allowed to do this? So think about it like you're multiplying both sides of this equation by the same number, or since we're multiplying it by 1/3, think about it like dividing both sides by 3. Right, since you're dividing the entire row, including the right side, you're basically just dividing the entire equation by 3, and you're not interfering with the other equations for now. So that's all that is, alright? Now the next thing you can do is swap two rows. Now there's no reason for me to do this really in terms of actually solving the equation, but I'm just showing you that you can do it if you want to, and I'm showing you what it will look like. So let's say you want to swap row 1 and row 3. That's exactly what it sounds like. You just rewrite row 3 at the top. Leave row 2 unchanged and rewrite row 1 at the bottom. And the reason you can do that is because it doesn't really matter what order these equations appear in, right? You're not going to change the outcome of what each variable is equivalent to. So you can rearrange the order of the equations however you want, but you cannot rearrange the columns, only the rows. Alright. The last thing you can do is add two rows together. So let's say I want to do row 1 plus row 2. And again, there's no real reason for me to do this. I'm just showing you how you would do it if you wanted to. So you kind of have a choice now. You can either add them and put them in row 1, or you can add them and put them in row 2. And the other one, whichever one you choose, the other one stays the same. So if I want to put the R1 plus R2 in the top row, I can do that. I could do 1 plus 4, right? That's R1 plus R2. 1 plus 4 would be 5. Put that in the top row. And 7 plus 0 is 7. Then 0 plus 2 is 2. And 14 plus 6 is 20. And now the rest remains unchanged. So I'll rewrite that here, just so you can see what that would be. So that's the alternative version that you could have done. Okay? Now, the reason you can do that is because you can add the same thing to both sides of an equation. I could put a plus 4 over here and a plus 4 over here, and it wouldn't change the equivalency of the expression. Right? So, since we have an equivalent sign here, that means that both sides of the equation are the same value. So we can add this entire side to the left side of this equation, and this entire side to the right side of the equation, and it would be the same exact thing as just adding the same value to each side of an equation. So I'm just going to write all the row operations here for you to reference easier. One is scaling, which remember is just multiplying a row by a scalar value. 2 is swapping, which is just reordering the rows. And 3 is adding. Where you can add two rows together. So in the next video we're going to learn how to actually solve systems of linear equations using this method. Good luck on your test tomorrow, and I'll see you in the next one.